In this video, I want to do an example that I call the two blocks. I really like this example because it is particularly simple. There's very little algebra, but it simply cannot be done without utilizing Newton's third law properly. So it sort of isolates Newton's third law to be able to understand. It also allows us to start to use Newton's second law with multiple objects, and I can explain sort of some of the problems that can sometimes result in that process as well. But for the most part, it really illustrates how to utilize the Newton's third law, which is really the purpose of what we want to do. So this example is worth spending some time with. It's simple, but I'm going to go very slowly through it so you can really sort of extract all the proper information we want. All right, so we have two blocks shown here, A and B. They're in contact with each other, and I'm exerting a horizontal force F against block A. The information is given here, the force on A, 24 newtons, the mass of A and B. We're going to assume everything's frictionless, and we want to know what is the acceleration of these objects, and what is the normal force of block B on A. Okay, and so I want to remember sort of the way we want to solve problems in multiple steps. We start with good visualization, and that's sort of what we have here. We've got kind of sort of a picture. We understand. We know that these objects are going to move off to the right. I'm going to get a coordinate system here. I'm going to call that the right, the positive x direction. Also, I note that everything is frictionless, so everything is going to slide. The two objects are going to move together. I think I have a good picture of what's going on. In the next object, sort of the brainstorming side, is really how we is sort of that approach when we use forces that we outlined before. Sort of how we choose one object, find the forces, and utilizing Newton's second law. So how would we do this now that we have sort of two blocks? So the first thing that we want to do is choose one object. So I'm not exactly sure how to solve this problem, but I think forces are the relevant physics that's involved. And so I want to use what I've known with Newton's second law to try to solve this problem. And so to utilize Newton's second law, I know that the first thing I have to do is choose one object. So let's choose mass A. Okay. Next is I need to find the forces on that one object. Okay, so what are the forces on mass A? So I'm going to get out my little highlighter here, and my forces are going to be gravity, I know. So I'll say that's F of G. So what all is in contact with block A? It looks like there are three objects in contact with block A. So there's the ground, exerts a contact force on A, and I know that everything is frictionless, so that means the ground only exerts a normal force. And I'm going to say normal force of ground on A. And so that's what I'm going to identify that as. The other contact force is block B, exerts a contact force on A, and so there's going to be, I'll call that a normal force. Again, everything's frictionless, so I'm going to call this the normal force of B on A. And so you can see how I'm using my notation here. I use my subscripts since I have two normal forces, and those subscripts communicate to me what the nature of the force is. The normal force of the ground on A, or the normal force of block B on A. I also have this sort of pushing force that I call, these are vectors of course, that I call F. What kind of force is that? Well, it's just a contact force like anything else. And just this is the sort of thing that shows up often in books, sort of the disembodied force. I exert a force on block A. Well, what kind of force is that? Well, it's just a contact force. They just haven't shown the object involved. You can imagine that there's some person or some object that's that's in contact with A that is exerting a force of magnitude F. So don't be confused that this is some new type of force. It's just a contact force, and but it's often, just to simplify things, it's shown without the agent in the picture, just the direction of the force itself. Okay, so these are the forces on my object. And so the next thing I want is to set these up with a free body diagram. All right, so let's go over here with a free body diagram that starts with a dot, and then the forces start with their tail at the dot in each direction. So gravity is down. The normal force of the ground on block A is up, because it's perpendicular to the surface from the agent to the object. The agent is the ground, the object is A. So there's this contact force that's pushing it forward that I call F. And then there's the normal force of B on A. And it's normal, the contact force, and points from the agent, which is B, to the object A. So remember, this is, I choose one object. And so this is the object mass A. So I'm only looking for the forces on A by all the other agents. And so my free body diagram only has the forces on block A. Okay, so the next thing is we want to vector sum the forces. All right. And you might notice that I have already seen ahead that some of these forces aren't really going to be necessary because everything's frictionless, but I just want to put everything there at the start, and we'll see sort of how the problem simplifies here in a minute. Maybe you've seen that already. Okay, so now I want to sum the forces. So I'm going to say, F is this pushing force. It has, I need the rest of my coordinate system here. I already said that sort of x was in this direction, so we'll call this plus x, and the up plus y. Got to have a coordinate system on your free body diagram. Okay. So F has it's entirely in the F direction. So its entire magnitude, which is F, is in the positive x, and 0 in the y. So what about the normal force of the block on A? Well, its entire magnitude is also along the x-axis, and from my coordinate system I see that's in the negative x direction, nothing in the y. And so then I have the force due to gravity, which has nothing in the x, and its entire magnitude is in the y, and from my coordinate system I see it's pointing along the negative x-axis. And then I have the normal force of the ground on A. It has nothing along the x, and its entire magnitude is along the y, and it's in the, not 0, but plus n in the positive y direction. So I'm going to vector sum these forces together, and then I want to set equal to the mass of the one object times A of one object. And these are the sort of things I highlighted when we first introduced the second law, and now it really becomes important. And what I mean by this, so I vector sum these forces. What are these equal to? There's not just ma, it's equal to the mass of block A times the acceleration of block A. Again, Newton's second law says the vector sum of all the forces on one object is equal to the mass of that object times the acceleration of that object. Right. And so we know from then the context of the problem, our visualization, that these two objects are just sliding along. So its acceleration in the y is equal to 0. And then it has some acceleration along the x direction. So just the magnitude of the acceleration A times the mass of block A along in the x direction. So now we have we can come up with our relationships. Well, by looking at the components of the vectors, and in the y direction, we essentially have that the normal force of the ground on A is equal to mass of A times g. And then in the second one, we have that this pushing force, contact force, minus the normal force of B on A is equal to the mass of A times the acceleration of A. Right. And so I think we sort of see where this is going. This first equation introduces this unknown, the normal force of the ground on A, that isn't even included in the second one, but it doesn't seem to play a role. All it says is it's equal to the gravity, but it doesn't contribute to a frictional force or anything else. And so we see that this equation probably isn't that useful, but we got it anyway. This is sort of our key equation. It links two things that we know, which is the magnitude of this pushing force, the mass of A, with the two things that we want, the acceleration of A times the normal force of B on A. The problem is we only have really one equation worth using. You might say we have three unknowns and two equations, but this normal force of the ground isn't something that we want to know anyway. And so what we really have is sort of two unknowns in one equation. So we don't have really enough to solve yet, and so we have to collect more information to develop more relationships between our problems. And so the approach then is to choose another object. Remember, everything we had here was just for mass A. So the obvious choice then is we choose another object. In this case, choose mass B. All right. So let's go through the list. First of all, we've chosen our object, that's mass B. Now find the forces on our first object. So our forces are the normal force of A on B. Let's go up and look at our picture here. So we're going to have gravity, and we're going to have then two things are in contact with B. The block of A and the ground are the two things that are in physical contact with B. So we have the normal force of A on B, this normal force by block A on block B. And then we have the force due to gravity and the normal force of ground on B, sort of the normal by ground on block B. So probably the most important thing to realize about this stage is what force is not here. The force that's not acting on B is this force. That force is only in contact with A. There's some object associated with that force, contact with A, and it's not touching B, so that force does not act on B. All right, so now we have a forces. Let's do a free body diagram. Did purple before. And to be honest, I think I can predict again that the normal force of the ground and gravity probably aren't significant. But, doesn't take too much time to include them now, just for completeness to sort of see how it all fits together. So we have the normal force of A on B. Remember, now that my object is mass B, the agent is mass A, and the agent exerts a normal force perpendicular to the surface. So that points now here in the positive x direction. And then the normal force of the ground on B, force due to gravity, acts in a similar way. All right, so now let's sum the forces, do a vector sum. And our vector sum then, we have the normal force of A on B, and that has some magnitude, A on B, all in the I hat direction. Then it's positive given my coordinate system. Our force due to gravity, nothing in the x, and that gives me negative mass of B times gravity in the y hat direction, normal force of the ground on B, 0 I hat plus magnitude G on B in the j hat. So these are my sum of the forces, and now I can set equal to the sum of the forces on one object, which is mass B. So now the last part is to set the sum of these forces equal to the mass of that one object, which is mass B, times the acceleration of that one object, which is the acceleration of B. So we know from the context of the problem that there's no acceleration in the y direction, and that just leaves us the magnitude of the mass times the acceleration in the x direction. So now we have two relationships, again, a similar relationship to the other one. The normal force of the ground on block B is equal to the mass of block B times gravity, and which introduces another unknown in the equation, so that's probably not so useful in the end, as well as the normal force of A on B, which is equal to the mass of B times the acceleration of B. So again, this is one of those where I really have done more work than I necessarily had to if I was really familiar with these. I might have seen right away that without friction, the only relevant dimension was the x dimension, and I might have worked entirely in the x dimension instead of keeping track of all the y-dimensional forces. But if you're not that familiar with these types of problems, you're never really harmed by being careful and keeping track of everything. But so now we have a second equation that contains information that's important. So we have a normal force and the mass of B times A. So let's bring our other one down here. So we have the F minus the normal force of B on A, mass of A times the acceleration of A. So it's important to note that at the moment we have two equations and four unknowns: acceleration of A, acceleration of B, the normal force of A on B, and the normal force of B on A. And so the first thing that we can identify is that the normal force of A on B and the normal force of B on A are Newton's third law force pairs. Here's my acronym for Newton's third law force pairs, because I can construct our magic sentence, normal force, right here, normal force, block A on block B, and the Newton's third law force pair is a normal force by block B on block A, which means I can establish a relationship between these two forces, which is the normal force of A on B is equal to negative the normal force of B on A, equal in magnitude and opposite in direction, which means their magnitudes are equal. The magnitude AB is equal to the magnitude BA. So that gives me a third equation, and I'll just let that equal to just an n, a third equation that these two magnitudes are equal. But that's not enough, is it? I still have to relate the accelerations between mass A and the acceleration of mass B, because Newton's second law only gives me accelerations for single objects. However, going back to my visualization step as how I pictured the problem, I understand that by pushing on block A, where everything is frictionless, that A and B are continually going to be in contact with each other. They will be in contact for the entire problem. And as long as they're in contact for the entire problem, that means the acceleration of A is equal to the acceleration of B, which means, of course, their magnitudes are equal. Their magnitudes are equal, and I can just assign that to some value A. So what would this mean? Where did this come from? You need to recognize that there is no equation for this. There's no law of physics for this. This relationship, which was necessary to solve this problem, comes from the problem itself. And so this is an example of where you have to be able to extract information and logically deduce relationships from the context of the problem. Now, you might have not realized this, and you might have erred with not specifically identifying that this A is only on block A, and this acceleration is only a block B. If you just sort of not thought about it and just set them equal to each other, you would have gotten to this point to say, oh, look, they're both just A. The problem is that's not always true. You can have objects that interact with each other where their accelerations are different, but you can still determine the relationships between the accelerations of the separate objects from the context of the problem. And so this is an important part of solving these problems, an important step you have to take. So in this case, we find that the accelerations are equal in magnitude and direction. All right, so now we can use these two equations to substitute into our equations that we got from Newton's second law. And we have that N is equal to mb times A, and minus N is equal to the mass of A times the acceleration. So I'm starting. I'm going to take one more moment here. I'm starting to say this a little wrong. Remember, when I write A, I mean acceleration. So I have two A's here, but they mean very separate things. So it's always important that when you write down symbols, that your mind reads what those symbols represent. So this first equation is not N equals MBA. It's the normal force between each object is equal to the mass of B times the acceleration of each object, which happens to be the same. And in this equation, the force on block A minus the normal force between each object is equal to the mass of A times the acceleration of each object, which we found to be equal. So make sure that you don't just read the symbols, that you read what the symbols represent when you look at them. All right, so I can substitute the first equation in for the second, and I have the force then is equal to the mass of B times the acceleration is equal to the mass of A times the acceleration. And then I can solve this, bring this on the other side, and pull out the acceleration. And now I can solve for the acceleration then, which is the force over the sum of the masses. Our original force, we said, was 24 newtons. Our masses were 10 and 2, so that's 12 kilograms, and so our acceleration was 2 meters per second squared. And now I can put that into the normal force on B on A, which is equal to N, is equal to the mass of B, which is 10 times the acceleration, which is 2, is equal to 20 newtons. All right, so this is the solve part of it. Everything up to this point was brainstorming, but once I got my 4 equations, now I can get into the solve mode, and so now I've solved. And the question is now, do I think this answer is right? And so let's go to the check mode where we can sort of verify what's going on. First of all, consider the whole thing as one object. Now that sort of is hinted at from this expression right there. Since these objects are in contact with each other, think of this whole thing as one object. If that whole thing is one object, what are the forces in the x dimension? Forces in x, in the positive x dimension, there's only one. That's F. So if I do the sum of the forces equal to mass A, the mass of the one object in the x direction, I only have one force, and that's F. So that's equal to the mass of that one object, which is the total mass, times the acceleration of that one object. Well, the total is mass A plus mass B, and the acceleration of the combined system is just A again. It's the individual objects. So A is equal to that force over the the force over the sums of the masses. Also, now let's just look in one dimension at each object again. Let's look at mass A. What was its net force in the x direction? So as there is a force from this direction, there is a normal force of B on A. And so call this the positive x-axis. So that was 24 minus the normal force of B on A, right? It's got the sandwiched between these two objects. And so we calculated that to be 20, and that's equal to a net force in the x direction of 4, which is equal to its mass times its acceleration. So that makes perfect sense. If we look at mass B, there was only one force on it, and that was the normal force of A on B. And so that's 20 in the x direction, which is equal to its mass 20 times its mass 10. Its mass was 10 times its acceleration, which is 2, which was 20. So that makes perfect sense as well. And so look how valuable this is by sort of checking from these 3 examples and how everything is internally consistent. I can be completely positive that these are exactly the right answers. All right, I've really taken a lot of time to do this one problem, which really is one of the easier problems, but I think this is so valuable to take your time to understand. And so the first is we've looked at the sort of the 4 steps, how visualization, brainstorm, solve, OLVE, and check. And then how with 2 objects, how you look at each object and apply Newton's second law for each object independently. And that gives you relationships between all the terms for each object, the forces on each object times the mass of each object times the acceleration of each object. Then how we use Newton's third law to establish relationships between the forces on the 2 objects. It was here where we were able to establish a relationship between the force on one of the forces on mass B and one of the forces on mass A, as well as using logic and the context of the problem and our visualization and our picture to be able to extract more information that was allowed us to establish relationships between the parameters of the problem. In this case, it was the acceleration of A and B. And then all of that led to then solving and making sure that we had the right answer. And so this is certainly took a lot of time to do this slowly, but I think the time on this problem will save you a lot of time later in in saving you the frustration for future problems.